powerful technique for exploring how the solution will change is setting up a dual problem. First of all, let's look at our standard problem again, doing some constrained optimization. For historical reasons, instead we'll look at the minimum instead of the maximum. And we want to start exploring what happens to that minimum value as you change b. Being precise about what the problem is exactly we're looking at, this set of numbers over this constrained set. The constrained set will break into two pieces. We'll call that set capital X, and we'll call that set capital X of b. So the problem we're looking at is to minimize function values over this constrained set. In shorthand notation, this is some number that depends on b. We'll call it phi of b. The primal problem then, p of b has solution phi of b. We'll set up the Lagrangian, and from the Lagrangian we're going to derive a dual problem. The Lagrangian introduces a new variable, the dual variable, and I take the inner product with the constraint. Since we're dealing with vectors, the vector inner product of the transpose. The Lagrangian is a penalty method. A penalty method is a way of taking a constrained problem and making it an unconstrained problem by introducing new variables. The minimum of the Lagrangian over all x is then related to our primal problem. I don't know the minimum exists, so infimum. Shrink the set, raise the minimum. But on the constrained set, h equals b, and the lambda term drops. So I'm just at the minimum f value, phi of b, which of course then is less than or equal to all other f values for feasible x's. Since I'm taking the infimum over all x's, lambda is the only variable left, so that's a function of lambda. I'll constrain the lambdas to be vectors where this function is defined. A fairly weak constraint. Phi of b is independent of lambda and is an upper bound for g, so it's an upper bound for the maximum. This is our dual problem. Maximizing g of lambda over this basic set of lambdas. Our goal is to find conditions to make that inequality an equality, so that the optimal dual will be the optimal primal. Taking a closer look at what I mean by that, the Lagrangian, if I restrict my attention to feasible x's, I remove the lambda dependence. The Lagrange sufficiency theorem for the primal problem given any feasible x, if I can find a lambda so that the Lagrangian at that lambda is g of lambda, then that feasible solution must have been optimal. This theorem essentially just gives you the conditions for when your maximum g is your minimum f, or gives you sufficient conditions, I should say. Looking at the string of inequalities, let's put in exactly what this one is again. If I'm at a minimum value for f, it's a feasible point. I plug it into the Lagrangian. Optimal f value, h minus b is 0. So it's just the optimal f value, phi of b, which is less than or equal to any other f value, which is the Lagrangian value for all feasible solutions. There's two inequalities in this chain. We want to collapse both. X star doesn't do anything, but now that X star is fixed, we find a lambda star that will collapse both inequalities. This inequality must be an equal, and this inequality must be an equal. So there are sufficient conditions for the primal problem and the dual problem to have the same value. In terms of labeling, the primal problem is called a strong problem or a strong Lagrangian problem. If the optimal dual value is the optimal primal value. Otherwise, our primal problem is called weak. We will see that linear problems are always going to be strong.